The objective of this lab was to determine the limiting region of the chemical reaction 0.2 molar KOH, which was a clear water-like liquid, with 0.1 molar CuSO4, which was a water-like liquid with a blue tint, to make potassium sulfate and copper 2 hydroxide at different ratios. The limiting region is the reactant that limits how much product is made.
For example, for every ice cream sandwich, you need 1 ice cream scoop and 2 cookies. In this theory, if you have 4 ice cream scoops and 10 cookies, you will have 2 cookies left, making the ice cream the limiting reactant.
Stoichiometry is based on the law of conversion of mass that states that any of one element at the beginning of a reaction will equal the mass of that element at the end of the reaction. This makes it possible to predict the amount of products formed if the chemical equation is known.
This relationship can be illustrated by mole ratio. The following information is needed to fully understand the lab.
For this lab, we started by sanitizing all of our materials with washing them out with municipal water, then with distilled water to get rid of all the unnecessary ions. This helped us get familiar with the equipment. The tools given out were 2 berets, 2 bray stands, 2 bray clamps, 2 funnels, 8 test tubes, 2 beakers, distilled water, 1 drying rack, and 1 stirring rod.
To start, we used the chemical CuSO4 that had a water-like consistency with a blue tint, and KOH, which also exhibited a water consistency but completely clear.
We added 5 milliliters of copper sulfate to each test tube and then 1 milliliter of potassium hydroxide to test tube 1, 2 milliliters of potassium hydroxide to test tube 2, and so on and so forth. As the liquid was added, we consistently stirred and made sure the 2 substances were thoroughly mixed.
Once all of the KOH was added, distilled water was included to even off the test tubes. Test tube 1 had 5 milliliters of CuSO4, 1 milliliter of KOH, and 7 milliliters of distilled water, all adding up to 13. Test tube 2 had also 5 milliliters of CuSO4, 2 milliliters of KOH, and 6 milliliters of distilled water. This pattern repeated until all test tubes had 13 milliliters of liquid. We set each test tube in a rack and waited 15 minutes while stirring consistently with a stirring stick to let the precipitate settle.
After the precipitate settled, we were able to see its form, observing its light blue opaque color moving easily if it moved in the test tube. We also observed the test tubes 5 through 8 started to change color to a darker green compared to the other precipitates in test tube 4 through 1 that stayed the same vibrant blue.
After observing, we measured the height of each precipitate in each test tube to find these measurements.
The graphs shown are the heights of the precipitates within the test tube. Notice how there is a gradual increase from test tubes 1 to test tube 4, and then a gradual leveling off once you hit test tubes 5 through 8. To make it even clearer, here's a line graph showing the rise and the plateau.
This is because of the limiting reactant. The limiting reactant in test tubes 4 through 1 is potassium hydroxide. As the amount of potassium hydroxide increases, the precipitate height increases, showing that the potassium hydroxide is in control of the height of the precipitate.
In test tubes 5 through 8, CuSO4 becomes limiting reactant. As the CuSO4 remains a constant level, so does the precipitate height.
This shows that the CuSO4 is the limiting reactant since it is in control of the precipitate height. Some of the mistakes we made that could have led to error within the experiment was that in test tube 5, we didn't add enough distilled water, meaning that not all of the test tubes were exactly the same level, which could have negatively affected the amount of precipitate that was made.
In our first experiment, we also did not mix enough, nor did we wait enough time to see clear results, so the numbers you saw before were from our second trial.